This paper addresses the problem of multi-robot task scheduling by estimating the demand for the task in a real-world scenario. We propose a stochastic, multi-agent, multi-armed bandit-based task scheduler which prioritizes the tasks based on the estimated demand for the tasks. To gain insight into the varying priorities of human task allocator in a multi-armed bandit scenario, we conducted a user study in a mixed reality environment which can be used to customize the resource allocation process. Multi-robot task scheduling gets complicated when heterogeneous set of robots accomplish a task by forming coalitions while executing their individual subtasks. It can be possible that a same robot is part of multiple coalitions for executing different set of tasks. Hence, a priority need to be assigned at the scarce resource to reduce the task completion times. We propose a demand-aware multi-robot task schedule that considers the demand from the environment to prioritize among the set of homogeneous robots while executing their subtask. Gazebo simulation with 20 mobile robots has been created to test the proposed approach. The coalition of robots perform pickup dispatch tasks as shown in the diagram, where a mobile robot carries load from the pickup point to a drop point. The tasks from the pickup point are generated based on demand probability. The assumptions involved in the problem are described as follows. The tasks are preemptive. The paired task allocation approach is used to allocate among the robot coalitions. The tasks are generated with a prior demand unknown to the task scheduling algorithm. Mobile robots that operate from a pickup point are homogeneous and cannot operate from other pickup points. The proposed approach utilizes multi-bandit formulation to prioritize among the mobile robots that are reaching the drop point. We propose a multi-armed bandit-based task scheduler with the following modules: tasks generated for simulating the demand from the environment, a fair task allocator that allocates the task among the robot coalitions, and a bandit solver to get priority among the homogeneous robots for scheduling. Our objective is to get a priority order among the set of homogeneous robots that are coming to a drop point. Task demand has been estimated by using a multi-armed bandit formulation. A multi-agent, multi-armed bandit approach in which agents collaborate among themselves by communicating their observed rewards has been proposed. The agents use a Thompson sampling approach and with an epsilon greedy exploration to estimate the task demand. Proposed multi-agent, multi-armed bandit solver estimates the demand of each arm as a probability distribution like the Thompson sampling approach, and the estimates are updated as shown. However, the policy of the agents follows an epsilon greedy approach where we have a continuous exploration. Once the reward is obtained, the agents share the rewards and choices to all other agents and obtain the priority order among the choices. We observed that the proposed demand-aware task scheduler performed better in terms of waiting times and demand-aware performance index compared to heuristic-based mean interference approach and rate monotonic scheduler and a standard first-come first-serve approaches. We will now show the mixed reality implementation of a pickup dispatch task, where a single mobile robot and two fixed-based robots are allocated tasks with a human in the loop. The mixed reality interface emulates a warehouse kind of scenario augmented on the real world as 3D holograms. There are two fixed based robots and hence there are two buttons that follow the user. Each button represents a command to the mobile robot to go towards a particular fixed based station. When the user pressed the button, the robot is going towards one fixed base station while avoiding the virtual obstacles present in the scene. It can be observed that these virtual obstacles are not present in the real footage in the top right corner. The robot is also observed to avoid the real obstacle in the scene while going towards the fixed based robot. The mobile robot uses ROS based navigation architecture with A-star algorithm and dynamic window approach as global and local planners. As the mobile robot reached into the workspace of the fixed base station, the load which was carried need to be pick and placed. The load is detected by the camera mounted on the top of the fixed base robot and uses classical computer vision technique to determine its position in the scene. Thereby we achieve multi-robot collaboration in a mixed reality via a human in the loop. In order to customize a human in the loop task scheduling process for a multi robot task scheduler, a user study was conducted to consider the priorities of a human task allocator. The results of this study can be leveraged to tailor the scheduling process accordingly. We conducted the user study in a mixed reality environment. The environment includes a warehouse model that has been created to match the spatial layout of an actual warehouse. The mobile robot can be controlled by a user from either inside the warehouse or remotely via a stereoscopic display that shows the warehouse layout. The users were asked to schedule the task for the mobile robot such that it can be teleoperated to move towards virtual reward stations displayed as holograms. The reward stations follow independent identical distributions with varying parameters. The user study was conducted for two users, a male and a female, over Bernoulli and Gaussian distributions. The reward is displayed in green over the top of the station as a hologram through the MR interface. In the figure, we observe that the fourth reward station consistently provides the highest reward. Although the goal of the user was to maximize the reward, the user did not adhere to selecting only the fourth station. The ellipses in the graph indicate the user choosing suboptimal reward stations to minimize the distance traveled by the robot rather than sticking with the station 4 to maximize the reward, which is their objective. Thank you.